Yeah, first of all, welcome everyone. I know I see many old friends and I see some new faces. I remember 2 years ago, Stan and I decided to try to apply for this lung program. This IPAM every year supported 2 lung programs. We tried 2 years. First year we lost to a quantum lung program. You probably can't understand quantum is a hot topic. But the second year we were successful, endorsed by the Scientific Advisory Board. And we have one tutorial week already a few weeks ago, and we have 4 workshops. This is the first one, okay? And so really, I'm so glad this, we have a physicist, mathematician, engineers, and material scientists together. I think that's the future of the university. It should not divide by each department, but by important problems, people work together from different angles of it. I thought personally for computational microscopy is really it's important. Historically, microscopy and the telescope play important role for the evolution of modern science and technology. I'm sure computational microscopy will become even more important in the future. So I'm going to talk about computational microscopy from coherent diffractive imaging and to atomic electron tomography. So I used some of the methods from CDI to AET actually really solve some important problems. Personally, that's my personal opinion. I think the really revolutions in microscopy, imaging, diffraction field. From optical microscopy, when we were in high school, we turned the knob. That's our concept. Most people, the concept of microscope, just turn the knob, get a magnified image. But it's not completely different, right? It is a super fluorescence microscopy, CDI, electron microscopy, X-ray crystallography from micron to angstrom, but also time from minute to attosecond. Margaret gave the talk today is a microscopy for tomorrow, and then tomorrow will be an ultra-fast. Attosecond light travels 3 angstrom per 1 attosecond. So it's extremely fast. So this is completely different from just turn the knob. So you need a very sophisticated software or computer algorithm to help us to extract as much information as possible, right? The reason I believe the revolution is because of brilliant X-ray sources. We all heard talks about X-ray free electron laser and advanced synchrotrons, diffraction limited storage ring, and aberration collected electron microscopy, and also powerful imaging methods, superluminous fluorescence microscopy, cryo-EM, CDI, and others, and high dynamic range detectors play very, very important roles. I remember first time many years ago I visited Swiss light source, and some physicists used the detector developed the CERN to X-ray community, and that make a bigger splash. I think the cryo-EM, they got Nobel Prize because the detector play a very important role, because you want to count single photon, single electron, and also advanced algorithm, big data, fast computing, fast computers, and deep learning. We will hear a few talks about it now in this subject. So now, microscopy play a very, very important role, as I mentioned, right? Now, if you have a chance this time, there's a place near Caltech, Pasadena, called Huntington Libraries and Gardens. There's some old books, okay, they're called libraries. So one of them written by Robert Hooke. And amazingly, he built a microscope in 1670, and then he looked at all kind of different biological samples, and he looked at a piece of cork, and he found this kind of a compartment, so called a cell. So the cell, the terminology was first adopted by Robert Hooke. And all this lens-based microscopy has played very, very important for, you can name it, right? This over the last 3 centuries, lens-based microscopy, such as optical, phase contrast, fluorescence, confocal superposition, electron, has played really important roles, right? But there's another way. Many of us from the CDI community, we know there's a phase problem. Phase problem, if you take the image, this is actually one of my students did it, and you just take a Fourier transform and you switch the phase, you get the phase actually more sensitive to our eyes more sensitive to the phase. So this is how to get the phase information. That's actually now it's beyond get the phase information, but really try to get high spatial resolution ultra dynamic. That's all play very important role here. So CDI is really, I think it's a unification of a diffraction imaging microscopy. You can think about it, right? It's really, the microscope based on, you can think of Young's double slit experiment, get an interference pattern, and then we get the phase. So this is diffraction, and also imaging, and also, replace the physical lens with microscopy. So it's replace the physical lens with a computational algorithm. So you can think it's a unification of diffraction imaging microscopy. I thought that the future is really even brighter because of the sources, coherent X-rays, electrons. The electron community actually now is picking up. They actually learn a lot from the X-ray community. I'm actually very glad now. So we learn from each other. This is why cross-disciplinary. As personally, I'm going to talk about two subjects. I learned so much from, I feel I'm even more successful by applying some of the methods to electron microscopy because there's always a blind spot. Now, everybody sitting here, right? We always like it to see old friends because that's comfortable, make it comfortable. We have a personal kind of a preference. We want comfortable. We don't like uncomfortable. But by my personal opinions, for doing science, you have to be comfortable with uncomfortable. Then you can make important discovery. This is just like in our community, we always face retrieval. We find a global minimum. If you trap the local minimum, if we're comfortable with local minimum, always trap a local minimum. You want to get a global minimum, you have to be comfortable with uncomfortable. You have to go over the barrier. That's just my experience. It's why people working together, it's really great. Stan and I have collaborated for years. At the beginning, we have a language barrier because math, everyone knows they use equations, they use symbols we're not familiar with. And we physicists, we have different training kind of a background. But after a while, we learn from each other, and we find actually something very obvious for them. It's not obvious for us. Something very obvious for us is not obvious for them. So we learn so much from this. So this kind of after this experiment, when I was a student, Chris was actually in the Chris Janusz group. We didn't expect this field. Probably Chris also didn't expect. Janusz didn't. Also, David Seaborg didn't expect this field actually have a big impact on many different. If you look at the original paper, we thought about for imaging biological cells. That's our goal. We didn't see anything else, but have a big impact. And since that in the last decade or so, this CDI method has really been developed dramatically, and Margaret and in also in Robinson also here. So we Chicago I couldn't be here in Japan because of COVID. And we wrote review articles. There's the original CDI tachography is also got scanning CDI. John Rodenberg played an important role, developed, pioneered this. And also the black CDI actually the pioneer of this field. So there's a more actually, also in optical light microscopy, they call it Fourier tachography. It's become a very important field. I just went to Caltech workshop. Fourier tachography is light microscope become bigger deal in that field. So and also electron tachography become, right? So this is dramatic. So in the following, I'm going to show some of our recent results, actually some in 2018. So relatively new results, okay. So in 2018, we developed a sort of in situ CDI. So what's the difference between tachography and in situ CDI? Everybody, tachography, you just scan the beam relative to the sample, every time overlap, the redundancy. So all this phase retrieval, measure the unknown variables and number of equations. You want to somehow this kind of intensity, also nonlinear equation, but it's kind of you measure more unknown variables than the equations than in principle they can be solved by iterative algorithm. So the in situ CDI we try to understand the dynamics. So we use a region, one static region, the other one dynamic region. And then we measure the interference pattern. So you can see tachography use partial overlap region in the space domain as a constraint. So in situ CDI use partial overlap region in the time domain. It turns out to be actually very powerful. So we can deconstruct both the complex wave and also as function of time. So I'm going to show you some, we demonstrate some experiment to use optical laser. And this actually shows the lead dendrites growth on the electrodes during the battery cycle. These are all in liquid. So, and you can see this is reconstruction by the in situ CDI algorithms. It's single shot, but here is tachography, you have to scan it. You want to scan it, if you when we zoom in this region, you can see the blurred because you scan it takes some time to but here is faster. So in principle, limited by flux and the detector. With upgrade APS, AOS, and SLS2, those flux will not be a problem. Detector is rapidly developed, so I think this has good potential. You can see actually with the line scan, you can clearly see actually better reconstruction. And we also tried the biological cell, and this the tumor cell fusion in aqueous solution. Now this is all done in optical laser. Okay, we just did. You can see this cell actually two cells fused together, so we can really get the phase. And the advantage is we can capture dynamics. Although the dynamic is slow, but we just for demonstration, this kind of a concept, it's actually turned out to work very, very well. I also want to show some work with attosecond pulses, as I mentioned, attosecond science. So attoscience actually is become a bigger field. Some of the pioneers, one of them here, and Margaret, and Paul Corcoran, and Klaus, and those are people really pioneer, including Margaret and Henry, and attosecond science. And one of the issues of the attosecond science is related to uncertain principle, because this delta E energy, delta E time, delta T is larger than h bar over 2. So if delta T is attosecond, then delta E become very large. The broadband, really broadband. So this so far attosecond science is spectroscopy. Okay, if you ask Margaret, she will tell you a lot about spectroscopy. But I think the imaging that we have some imaging coming in. The imaging would have provided much more information, right? But the imaging with broadband, this is broadband, really broadband. The wide beam is delta E over E is like 50%, but here is over 100%. And think about it, right? If you microscope, you usually have the sharp, one single lambda you can focus it. With broadband, you blurred. Just like in older eyes getting blurred image. You want a sharp image, you have the single wavelength. This actually so we developed algorithm, try to disentangle this kind of information. So we did this kind of a Tychockley CDI, use attosecond pulses. We did a simulation, okay, use this one, 100%. And you can see diffraction pattern, speckle pattern is very blurred. There's no speckles, because it's a complete broadband. And now if we know we can develop an algorithm, can simultaneously reconstruct the probe and the spectrum and also the images. So this is, we was very surprised, and it actually worked out very, very well. We posted everything online, so you're welcome to try it out the code. So we did some simulation and then experiment. And the simulation is just attosecond pulses with this similar structure, and then with some absorption edge, you want to see whether it can distinguish different elements. And you can see diffraction pattern it's not like a speckle. It's more kind of very blurred image. And then we reconstructed the spectrum. You can see the red corresponds to true spectrum, and the green corresponds to recovered. You can see very well. We recovered 17 different positions. Okay, 17 different positions. And then we did LED experiment. LED is like delta E over E about 50%. Okay, it's not 100%. We can recover it. Now, this requirement is overlap has to be very, very large. There's no free lunch. You have to get something from something. So in order to get so much information from the measurement, you have to do a lot of measurements. So measurement overlap is relatively large. We have like a 98% overlap. That help to disentangle this information. And here shows the one, okay, the first simulation. You can see, I just only showed 3 of reconstruction. This is original, okay, the different wavelengths. You can see the field of view getting, this field of view getting smaller, but resolution getting high, because we use the same pinhole, okay? And the field of view is kind of a same pinhole, and then we get a reconstruction. So this actually, you can, the resolution is high, okay? The short wavelength resolution is high, because it's with the same pinhole. And this original image, this is a reconstructed image from single scan, which is one scan, okay, one series of diffraction patterns. And here we reconstruct the probe. So we reconstruct 17. And here I just use 3 of them. And then we did a kind of absorption. The boron on the aluminum, we did a simulation. This boron actually is absorption at 6.6 nanometers. And you can see at the 17, we show 17. This is actually it's below the absorption edge. And then at 6, suddenly the CI pops up because of above the absorption edge. It showed again, and this is reconstructed the spectrum versus we measure the spectrum. This is for LED experiment. So you can see this actually it's quite a powerful kind of experiment. And here we did LED experiment. We did some test samples. This is different wavelengths. This is a probe, reconstruction probe, and this is zoomed in image. And again, so we put everything online. So everybody interested, you can go to the code and the data online. You can do analysis. Okay, so far I talked about the CDI. So I want to do the atomic electron tomography. I used in around 2011. I realized some of the algorithms, iterative algorithms, solved phase bond can be used for tomography reconstructions. So we use this iterative algorithm. Here, the tomography, There's no phase problem. But we try to get the best possible reconstruction from a limited number of projections, right? The projection cannot get infinite number of projections, radiation damage or experimental constraints. There's a missing wedge problem. You cannot tilt plus minus 90 degrees, such as, right? All these kind of constraints. So we try to get best possible reconstruction from the limited data or noisy data. That's always the key, right? What's the best possible? You cannot get a perfect reconstruction, but what's the best possible reconstruction from limited data, right? So we developed this atomic electron tomography. The goal is try to get 3D atomic position without assuming crystallinity. This is going back really, David here and I had many chat when I was a graduate student. I was always interested in amorphous material, disordered materials. Now, crystallography has to be great, but solve the crystal structures, right? And this, but amorphous structure. So over the years, we really solved something important. We can see something nobody's seen it before. Because like, example, glass, glass, what's the atomic structure of glass? Just people talk about it, but people thought it was impossible to solve it. So we actually developed this kind of, continue to develop, collaborating with Stan's group and develop new algorithms, and we push the limit. I really just feel push the limit to solve the important problems. So I'm going to show this, why this question, always in my dream when I was at graduate school, what is the amorphous material structures? Liquid-like, for example, another structure. This is important to read the atomic structure crystals. This actually first atomic structure was solved. It's a table salt everybody used in the morning, had breakfast, and a diamond by Blacks, 1913. And they both got Nobel Prize 2 years later. This is diamond. And now this is actually kind of most for solid deformed, this is called FCC structures, or HCP, face-centered cubic, or hexagonal closed packed. This actually turns out Kepler, the famous Kepler, the astronomer, he has a conjecture that the FCC and HCP highest packing density is 74% about it. And it was proved almost more than 300 years later by Hales, and he actually made it. It's a bigger deal in the discrete math. So this is what the FCC. You have it's a Billy balls. Okay, you pack the first layer, and then the second layer you use a black one. You just between the three put on, and then the third layer you have two choices. One is A, the other one is C. Right? A just this layer is same as the first layer. The second packing is A, B, C. So this is called FCC. This is called HCP. So it turns out this is the highest density packing. Okay, that's kind of later we'll also come back to this a little bit. And of course, DNA double helix and the first protein structure solved. It's all based on the crystals, right? But if you look at around our nature, liquid, solid, two fundamental state of matter. Liquid and amorphous solid are more ubiquitous than crystalline feature compound. Our body is made not a crystal structure. Although cryo-EM can solve the atomic structure, but it needs many identical copies. I'm always trying to push without identical copies. Ideally, if one can get 3D atomic structure of a cell, whole cell, this will revolutionize life science biology. But the question is whether it's possible, whether it's a fundamental limit or the technology limit, right? So we look at some of the amorphous structures. I'm going to show some results. Now, also in 1952, Frank hypothesized that icosahedral order is a prevalent atomic motif. He just calculated icosahedral order should have locally. Actually, icosahedral order has a low packing density than FCC and HCP. But a long range FCC, HCP win. So because the icosahedral 5 order, you cannot fill in 3D space. So quasi-crystal is icosahedral. You can actually fill in some quasi-crystal, okay? And also in 1995, Philip Anderson is a very well-known physicist. He said that the deepest, the most interesting unsolved problem in solid state theory is probably the theory of the nature of glass and glass transition. And the reason is just very difficult experimental probing. Currently, the method is use diffraction, use pair distribution function, or use computation, molecular dynamic simulations, or use DFTs. Okay, so here I'm going to show the icosahedron. Icosahedron is you can see 13 atoms, 20 faces, 12 5-fold. Each one's 5-fold. You can see 5-fold. Okay. Okay? And I want to show there's a pentagonal bipyramid. Pentagonal bipyramid is 5-fold, 1, 2, 3, 4, 5, and one top, one bottom. So it turns out that 12 pentagonal bipyramid form this icosahedron. And if you put this atom in the center and all this other atom is 12, then form. So basically, each atom and the edge atom at the vertex form this pentagonal bipyramid. Okay, this is gonna come back. So Frank hypothesis, this become a classical paper. If you search this car, very well cited. This pentagonal bipyramid is. So here is the icosahedron. Okay, icosahedron has a symmetry in nature. A lot of violets use the icosahedron order. And so here shows one amorphous materials. This is more than I think 20,000 atoms. This is like a small protein. It's a protein molecules. And you can see these atoms. There are some actually the darkest colors actually are the nuclei, but most are just amorphous. Now we did the reasons we can do quantitative analysis because we can identify the coordinates of each individual atoms. So it's very quantitative instead of qualitative. And then we can do the analysis, see how the arrangement of the 3D atomic packet. So we found something interesting. And we first do some analysis, just basically, right? And take the Fourier transform, and you can get this like amorphous structures. We also did a measurement, and this also just like, and we did the tantalum thin film, as a little small region, more than 8,000 atoms. And here is actually 52,000, I said 52. So it's like a relatively sized protein structure. And then we should pair distribution function, actually they are just like amorphous. Now the pair distribution functions look at the atom and the neighboring, right? The first peak corresponds atom as the first neighboring and the second neighboring. And we also did molecular dynamic simulations. The tantalum liquid actually very similar. So we also observe this amorphous solid structure, this atomic structure, very similar to liquid structure. This is very I mean, the reason we can see this is because nobody can look into get the 3D. We are the first to really get all the atomic positions. And then we also did a Voronoi index. Especially everybody heard about the war of the Ukraine war. This Voronoi, Georgy Voronoi, was Ukrainian mathematician. He passed away, but he developed a method how to find the short range order, atom and the neighboring atom. So he found the atom and the nearest atom, how to find the geometrical kind of the arrangement. So it's called a Voronoi index. And so you see the 4 numbers, 1, 2, 3, 4. The first, the 3-fold symmetry, 4-fold symmetry, 5-fold symmetry, 6-fold symmetry. So how many? Like 0 for 3-fold symmetry, 6 5-fold symmetry. Okay. So you can see this 0, 3, 6, 3 is the highest among all this. This is samples synthesized by different groups, a different method. This is physical vapor deposition. This is a chemical method synthesized, and they are quite consistent actually. And for the crystal structure, 0,444 should be more abundant. Okay? And then we look at this atomic packing. We found this atom form they call triplet. Each one corresponds atom, one top, one bottom. Okay. Or the quadrilateral bipyramid, we call it, or pentagonal bipyramid, 5, 1, 2, that's what I mentioned, okay? And or hexagonal bipyramid. And then we look at what's the percentage and find the pentagonal bipyramid always most of them. 5-fold always most abundant. 5-fold, so somehow the 5-fold, it's locally, it's denser than FCC, HCP. Just local minimum versus global minimum. FCC and HCP global minimum, right? So 5-fold symmetry actually. And then we look at how this 5-fold connected together. 5-fold becomes most abundant. And we found this vortex sharing. This actually, if you look at this one pentagonal bipyramid, there's 2 pentagonal pyramids share 4 atoms. Okay? This is form this is called vortex sharing. If you look carefully, the 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, and one top, one bottom. So they share 4 atoms called, and we use this represented each black dot corresponds to centroid, center of mass for each tetrahedron. Okay, for each tetrahedron, centroid of the tetrahedron. And this is what vortex sharing. And they form this kind of network. And here shows edge sharing. Edge sharing, they actually, in this case, they share 5 atoms, 1, 2, 3, 4, 5. the shear edge. So this each edge is connecting between the centroid of the two tetrahedron. Okay, that, I hope following. So we found this actually more abundant. The edge shading actually that's more this pentagonal biplane have edge shading. And we found this edge shading, they form this bigger network. It's called medium range order, like this one. They form this medium range order. And this is one example, the largest pentagonal, or the edge shading pentagonal bipyramid. The blue corresponds to tantalum atoms. The red, or the black corresponds to the centroid, the centroid of the tetrahedron, and the line, this orange corresponds to connecting them, form this 5-fold, symmetries. This is one example, but they don't form icosahedron. You see, icosahedron, as I said, you need 12 pentagonal bipyramid. So here I only have 8, 3, 5, 5, 3. And we never seen any 12. In all our samples, we never seen 12. And here's the size of this pentagonal bipyramid network. It's the largest 135 pentagonal bipyramid, this one. So we actually did molecular dynamics simulations and showed only if one become a glass transition, during glass transition, then they have some percentage to form this icosahedron. So you can see liquid. So that's our hypothesis, our model. Actually, we have some evidence, right? So when liquid transition from, just liquid to glass, they form this, at the beginning, they form this kind of a network, pentagonal bipyramid network. Each one's a partially filled icosahedron, not a full icosahedron. But then when you really transition to glass, and then they have more, formed completely this icosahedron. And we actually observe, in molecular dynamics simulation coupled with our experiment data, we confirm that that's the case. So, I mean, icosahedron is definitely, locally it's density packing. But when during the transition, they first form this pentagonal bipyramid network. That's understandable, right? You can see they connected together, and then when we found when all the atoms form connected together, and then some of them form full icosahedron. I hope it's very clear. That's kind of a understanding of this. I mean, we just know the reason that we can observe because we have the atomic coordinates. We can do quantitative analysis. That's, I think there's one physicist did some experiment, J.D. Bernal. J.D. Bernal was a thesis advisor of two Nobel laureates. I forgot. I forgot. But he was a British physicist. He tried to understand the liquid. So what he did, he used these small bowls made of stainless steel. Use these beads. And then he put in a bucket and then shake it. I mean, shake it, and then the volume getting smaller and smaller. And then he just, pour in some glue. Then all this ball glue together. And he asked the poor graduate student to just remove one at a time and map out the 3D position. And he actually published a few Nature papers about what's the packing of this 3D balls, try to understand liquid. So there's a few become classical papers. But now we can really look at the atom. We can get the coordinates. The precision is about 20 picometer precision. Now people ask us, how do we know the atoms are consistent? Because we actually did it very careful. We did a sequential experiment on the same samples and do independent reconstructions, and we get about 98% consistent. Not perfect. Some surface atoms are changed, but overall it's very good. And then we also did another paper. That paper published early this year, Nature Materials. And we also tried to answer what is 3D atomic structure multi-component metallic glasses. So there's a kind of a community. Before I work, there's a debate. I don't know our paper solved because we think that one model is correct. So they call it efficient cluster packing model. So the basic point is liquid amorphous glass atoms not randomly packed. They're not just like put all this stuff together, atoms. They have some kind of very interesting structures. So there's kind of a debate. One is by Miracle. He published a paper 2004, used indirect experiment method. So he believed there's solute and a solvent model. So each, you can this blue corresponds solute, and the red corresponds solvent. They form cluster. Each cluster is disordered, but the cluster form this called FCC or HCP kind of a FCC HCP like a MAO, short range order. MAO typically is a few nanometers. The long range order, the medium range order, right? Long range order is crystal. It can be meters, right? And there's another model by Shen et al. They form the icosahedral like MAO. So each atomic short range order basically is understand. Use some pair distribution function already understand. But how this atomic cluster, atom and neighboring atom, they pack together to form medium range order. There's a debate. So these claim they form this icosahedron like MAO. So each cluster forms icosahedron. Okay. So versus here is the FCC and HCP. So we did this experiment on the multi-component metallic glasses. There are 8 different type of atoms, and I'm going to show the movie. And because some of the atoms, the Z is so close, we divided them into 3 different categories. Okay, red, blue, and green. The red is a high Z. The green is a low Z. And we go slice by slice. You can see one thing very interesting. Red is more uniformly distributed compared to other 2 types. And that's the reason, actually, we did a quantitative analysis. That's actually turns out the red corresponds to solute, and the other corresponds to solvent. And you can see also there's some kind of a periodic structure here. There's some nuclei. Okay, so this is overall, most of the atoms are amorphous. So here shows the one slice. Okay, you can see some atom, the high Z corresponds to the bright, the more uniform distributed than other types, right? And then we also did some analysis in local bound orientation order. That just shows how close to amorphous. Now this should be, liquid should be here, okay? And this is BCC, this HCP, this FCC is here. So this is the bound orientation order is well used in the amorphous material community. Use MD simulations, they always use. And then use a pair distribution function. Okay, as I mentioned, pair distribution function. The first peak corresponds to atom and enabling atom. This is called atom and the second enabling atoms. Typically, they are getting, first peak is always high, right? And the second peak is getting small. And then we did a partial PDF with a type 1,1. Remember, we have 3 different type of atoms. We cannot identify all these 8 different types because some of the sensitivity of our method is proportional to Z, atomic number. Some Z just different by 1, so we cannot. So you can see 3,3, type 3,3. The first peak is here, second peak is high. What does that mean? That means actually the atom and the neighboring atom correspond to first peak. Atom and the second enabling actually more. So which means more uniform distributed. So this actually somehow consistent with the solute and solvent, because solute is, each solute atoms at the center, they form kind of cluster. And then this solute clusters, they form this FCC HCP. Remember, FCC HCP mathematicians proved that's the densest packing in nature. But this forms this kind of short range order, okay? Or the short range order, medium range order. And then we look at the SRO, short range order, as the Voronoi index, as I mentioned, right? How many, what's the kind of a symmetry, different symmetry. Here show some examples, 0, 4, 4, 4. For example, in this case, this should be 4 or 5 for the symmetry, okay? This is 0, 0, 12, 0. Anybody know this should be, what's this structure? Icosahedron, right? This is icosahedron, because 12, 5 for the symmetry. So 13 at 1 in the center, and each one is 5 for the symmetry. So this is 0, 0, 12. This is all from experiment data. So we can look at all the different kind of short range orders. Short range orders basically the community already, because they use some diffraction method, they can, the first peak, the DFT. But the medium range orders are unknown. So this is why. And we also there's 44% of 5-edged faces, because we add all these 5-edged faces, which means pentagonal bipyramid, right? In SR, but only 7% of all Voronoi polyhedron are icosahedron. So most are pentagonal bipyramid instead of from icosahedron. That's actually all consistent from all different samples. And then we look at how this SRO the connectivity, and they're sharing one atom. This is clustering SRO, okay? The connected, and there's 2, 3, 4, and 5. The most actually 2 and 3 are the most abundant. which is these two cases. And then we actually developed one of my students, and he has a lot of computation experience. So we developed an algorithm, the breadth first search. This algorithm have been used in a completely different community. We implement this algorithms, and we found this FCC-like, this each cluster form, all these clusters form this FCC-like. So we only show the central atoms, they form this FCC-like. This shows HCP-like. This is BCC-like. This is kind of MR, medium range orders, about like a nanometer, a few nanometers, over 2 nanometers in length from here to here. So this MR shows transitional but no orientational. So we confirmed the miracle model, but instead of the Nature paper on this MRO for the icosahesion, we didn't find icosahesion like MRO. And here shows this. We find actually a little beyond a miracle, because we also find BCC in a simple cubic. This is coexistent inside these nanoparticles. We call it like this is not a crystal, okay? Because there's no orientation order. Crystal should have orientation order, translation orders. And here we show the distribution of this. FCC and HCP more abundant, and there's also BCC and FSC. So we actually, based on our data, at least one data point shows this miracles model seems like more correct. And we didn't observe this icosahesion like MR. So in summary, I hope that my time is up. So I think the experiment, the CDR has been developed very, very quickly. I'm glad these people, actually a lot of applied mathematicians also interested in phase problem, because this is related, there's a lot of potential applications, right? So I'm glad that this field becomes such important for different directions. And we also developed in situ CDI and broadband CDIs to probe dynamic structures. And also, we can reconstruct so many different things, spectrum, structures, probes. And we also developed a soft X-ray vector tychography to directly observe topological magnetic monopole and probe their interactions. And then we apply some of the methods, I just know algorithms, instead of solve phase problem, but we try to get the best 3D reconstruction from limited measurement. We solve central order problems. So personally, I feel the future is very bright for this field. I want to thank many of my collaborators. Some of my group members are here. I truly they work extremely hard. And many of them, and also my collaborator Margaret Henry, here, and Lola. We're starting collaborating, and I really have some wonderful collaborators. And that's my students and my postdoc and Colin, Elisa, Eda, and Saman. Some quite a few actually. Some probably online. Yeah, thank you for your time.